Welcome back, and in this video we're going to continue looking at the alkenes and their reactions. So you're going to need your notes, and we're on page 13. So the first reaction we're going to look at is this electrophilic addition reaction with steam. So this works only with steam, so that means the water must be in the gas phase. Now you need a catalyst for this reaction. You can use concentrated sulfuric acid, but a better one to use is concentrated phosphoric acid, H3PO4. You get a cleaner product. So as this is an addition reaction, you only produce one product, and that is the alcohol. Now this can be defined as an addition reaction, or it could be defined as hydrolysis. Hydrolysis because lys means to break, and you're breaking that carbon-carbon double bond, and hydro simply means water. So you're breaking this up using water. So the equation for this reaction is straightforward. You're opening up this double bond here, and on each of the carbons of the double bond, you're adding, on one carbon of the double bond, you're adding an OH group, and on the other carbon, you're adding a hydrogen. So you need to be careful that you're only adding things across the double bond. So for example, if I have propene, from here I can make two possible alcohol products. I can make one here because I can add the OH group to the first carbon, and that would make propan-1-ol, or I can add the OH to this second group and I'd make propan-2-ol. So you do need to be a little bit careful when you've got unsymmetrical alkenes. The next reaction you need to know is this oxidation reaction with acidified potassium manganate. Now this acidified potassium manganate is bright purple, and it will decolorize on shaking. Now sometimes you'll see it go brown. If you do, it's usually because you've not added enough acid. You do need to add the acid to get the full reaction, but if it goes brown, it's still a positive reaction. So again, you're going to open up the double bond, but this time you're adding OH groups onto each of the carbons of the double bond. So this organic product has two carbons, so it's eth. It's an an because we've lost that double bond, so it's eth-an. And because I'm on carbon number 1 and number 2, it is 1,2-di-ol. Now this again could be classified in two ways. It could be classified as an oxidation reaction because you're using an oxidizing agent and you're actually changing the oxidation numbers of the carbons, or it could be classified as an addition reaction because you're adding across this double bond here. So we've talked about cracking in the previous pack, in the alkanes pack. But generally speaking, we crack our alkanes into shorter chained alkanes and alkenes. There's much more uses we can put the short chained to than the long chained, so it makes more useful products. So for this example here, we can take our long chained alkane and we can split it into this shorter chained alkane and ethene as one of my products. So this is a diagram of the practical you're going to see in class, and this is just cracking. So we're going to set up the apparatus like this. We've got at the end this mineral wool which is soaked in medical paraffin. So that's basically my long chain alkane. I've got my catalyst here. I can use a zeolite or I can use aluminium oxide. But notice it's the catalyst I need to heat. So you need to be careful where you're drawing this heat arrow, because it's the catalyst that needs to get to the right temperature. The residual heat will basically vaporize those long-chained alkanes. Even though the long chain, they still have quite a low boiling point. And we're going to collect the gas by the displacement of water. So you're going to see 3 tests done. The first test, holding the test tube upside down. You can vaguely, it's quite a difficult one to see, but you might be able to see a yellow sooty flame. The bromine water in the second test tube would decolorize. You could also try this with acidified manganate and you should again see it decolorize. Now the first sample of gas is always discarded because as you heat the apparatus, the air inside it expands, so the first test tube will contain a significant amount of hot air from the apparatus. The delivery tube is removed from the water before you stop heating. This is to avoid suckback. Cold water and hot glassware generally don't want to mix. The last reaction that you need to know for the alkenes is the polymerization. So these can polymerize into long-chained polymers. So poly means many and mer means a single unit. So these are polymers. You don't need to know the mechanism for this reaction, but it is a free radical mechanism in case you're interested in. What you do need to be able to do is to do the equation. So I take many, there's a little n here, of these single units, and I'm going to change them into this polymer unit. So this is a single polymer unit with a little n outside the brackets to show that it's a repeating unit. So I take many of these individual units. I'm going to open up the double bond, so this double bond is going to open up and join onto this one and have a join that way. This double bond is going to join there and to the other side, join again. So you can see how these single units turn into this repeating unit. The one students often get wrong is this one, polypropene, because remember, you're only adding across this double bond. You're not adding across this sigma bond here. So this is what your 3 repeating units look like. This is what 1 repeating unit looks like. You've always got 2 carbons in your repeating unit, because if you think about putting the double bond back, that is where the double bond would go, between those 2 carbons there. And then it's whatever was attached to the carbons is still attached to the carbons. So on that first carbon I have 2 hydrogens, and on the second carbon I have a CH3 group and a hydrogen. So you do need to be careful that you are only adding across the double bond. And here are some examples we've done for you on the next page. So do be careful of any groups which are attached to the double bond, that they stay attached to the double bond. So for example here we talked about propene turning into polypropene. This CH3 group remains attached to this second carbon. It doesn't matter what the monomer unit looks like, you should be able to draw the polymer chain based on it, because remember you're only interested in this carbon-carbon double bonds. And that's true for all of them. So some molecules we won't have come across before, but you're looking for the ene part of the molecule, because that tells me it's got a carbon-carbon double bond, and therefore it tells me that it's doing an addition polymer. So missing out the practical, which we're going to do in class, we're just going to have a look at the management of plastic waste. So we're moving on to page 21 of your notes. So as an individual, we can try and buy products which have less plastic packaging. We can use renewable shopping bags where possible. But the 3 main ways we can reduce plastic waste is recycle, incineration, and reuse for chemical feedstocks. And these are the main 3 ways we stop plastic waste going to landfill. You can convert the plastic into other materials, such as plastic bottles, which can be turned into carpets. The plastics do need to be sorted, and only some sorts of plastics can actually be recycled. The other thing you can do with plastics is you can simply burn them. You can incinerate them to produce energy. These are basically hydrocarbons, so they are a fossil fuel, however, and they can produce toxic gases from the pigments and halogens which are in the plasticizers. They also produce large amounts of carbon dioxide and water. The last thing you can do with them is we can break them down again into their monomer units, and then we can reuse those to make new chemicals or indeed to remake the polymers. The other ways that chemists can help is by developing biodegradable polymers. So these are ones which break down in the environment. They can also be used inside the body because they'll break down. The other way is we can remove the toxic gases which are produced by incineration, and this is important so they don't go into the atmosphere. We can also do a process called carbon capture and storage, where the carbon dioxide is also caught and not released to the atmosphere, contributing to global warming. So there are several ways that chemistry can help in reducing plastic waste, and this is just a list of a few of them. So we're on the last page of your notes, and we're looking at this spider diagram on page 23. So you need to be able to understand what all these processes are and the reagents and conditions needed for each of them. So here they are in a little bit more detail. So from our crude oil fraction starting at the top, we would do a fractional distillation to produce the alkanes, quite long chained usually, and then crack them to produce shorter chained alkanes and the alkenes. And that's done using aluminium oxide and a zeolite catalyst. We need high temperatures and a catalyst because you're trying to break strong carbon-carbon bonds. So you need both those things to get this to work. Going round clockwise, we have bromine in water. So do be careful that this is in water, and here you would produce the bromo alcohol. You would also probably produce a little bit of the dibromo, but that's more where the bromine is dissolved in an inert solvent or an organic solvent. It doesn't necessarily have to be hexane, it could be cyclohexane, it could be any inert solvent. And there we get the dibromo product. If we used hydrogen bromide, we've just here done the major product, 2-bromopropane, but you should also remember there is a minor product of 1-bromopropane. And you need to understand why this is the major product by linking it back to the stability of the carbocation. The reaction to produce the single alcohol group, functional group, is either known as hydrolysis or addition, and that's using steam, so the water needs to be, remember, in the gas phase, and we more normally use a concentrated acid catalyst, H3PO4, concentrated phosphoric acid. We can get the diol by doing the oxidation reaction or addition reaction using acidified potassium manganate, and that will produce 2 OH groups, one on each carbon of the double bond. Reduction reaction, again, or a type of addition reaction. This is hydrogen and a nickel catalyst at 150 or a platinum palladium catalyst at room temperature, and you're adding hydrogens onto each of the carbons of the double bond. Last but not least, this addition polymerization, where you're adding across the double bond using catalyst and high pressure, and it's initiated by this free radical. So you need to practice drawing out that spider diagram. So that finishes off the alkenes notes. They, along with the alkanes, make the hydrocarbons, the basic building blocks of organic chemistry. So until next time, take care, stay safe, bye-bye.